Yeah, okay, just I wanted to open the chat in case someone asks.
We can. Oh, sorry, I didn't mention this. So I can, if someone writes something in the chat, maybe I can interrupt you and I can ask the question.
Okay.
And yeah.
No, I think I'm now seeing the chat, so
Okay.
I can also read it if something pops up. So otherwise, you just say to me.
Okay.
Si lo quieres presentar, Juan, ya empezó el video.
Okay. Okay, well, thank you everyone for coming. Welcome to a new session of our category seminar at UNAM. Our speaker today is Alcides from the Federal University of Santa Catarina in Brazil, who was nice enough to accept our invitation and who will be speaking about non-commutative symmetries in higher categories. So the title of this talk is Noncommutative Symmetries, a higher categorical perspective. We will be reading questions from the chat during the talk. If at any point anyone wishes to be unmuted, please raise your hand and we will unmute you. There will be a questions round at the end of the talk, and we will be reading questions from our live YouTube channel. So yeah, please take it away, Alcides. Thank you very much.
Hey, thank you, Juan, for the invitation. My pleasure to give this talk. So I'll try to mix a bit of category or higher category theory with system algebras, operator algebras, which is my field of research mainly. So this talk is based on some, say, old works of my own and some co-authors, mainly Ralph Meyer, but also in one of them, also Chen Cheng, or two of them, Chen Cheng Su. It's also a geometer, also understands a lot about higher categories. She was involved at the beginning of this project, and we still want to do something more. Are you seeing the second page of my slides? Because I'm not, I'm moving here, but I don't see any, sorry.
We can only see the title.
The title, yeah, that's maybe something, I think I stopped sharing and share again because something strange happened. Sorry. I think it will not work. So I was already on the second page. This is the second page. You are now seeing the second page of the slides. So let me now try to move. If I move now, then you can see my movement, right? Okay, good. Now it's working. So I was saying that's based on some papers that I had, so almost some of them almost 10 years ago, in 2012, 2013, and another one. We had it 2013 already, but it was published only 2017. So all these papers are already published, and this is the talk is based on this, and they are all available in the archive. And as I was saying, we still have some things to do. We would like to improve some things in the future. I still didn't manage to do this, but let's start with motivation for this. So let's start with an example, which is a classical example of a non-commutative space, let's say, or system algebra. So non-commutative space now our field is also sometimes modeled by a system algebra. So non-commutative geometry. And so this is one of the classical system algebras that we study. So we look at the so-called irrational rotation algebras in general. We take any number lambda, could be rational or irrational, or I mean actually this parameter theta here. This lambda is e to the 2 pi I theta, and this theta could be rational or irrational, but it gets more interesting when it's irrational. So let's stick to the irrational case. And this is actually called the irrational rotation algebra. And also it's interpreted as the quantum torus because it can be, so it involves two unitaries. By definition, this is the universal system algebra generated by two unitaries that satisfy this relation. So they are not commute, they do not commute, but they up to this scalar, they commute, so to say. If this would be rational, then or integer, they would commute, and this would give the two torus. So in general, interpreted this as the non-commutative two torus or the quantum torus. So this is one of the most studied system algebras that we know. Was already studied by Riffiu in the 70s and even before that, I think. So, and also it has a model in terms of cross product. I'll talk about this in a minute. That involves an action of the integers on the circle, and this action is by rotation with this angle here. So this action is also implementing this quotient. We can take the orbit space, which actually is a group. We can view these powers of this number, this lambda here. We take the powers, and since this is irrational, all these powers are different, and this gives an embedding of the integers into this group, into the circle group. So we can also look at this quotient as the quotient group. And this algebra should also be viewed as this as algebra of, I'll say, algebra of functions on this quotient group. This quotient is badly behaved. That's the point, because actually here, since they are again, it's irrational. This subgroup is dense in the circle, so this is a quotient by a dense subgroup, and so the topology of this space is trivial topology, although this is an infinite space. So topologically speaking, this is a bad space. So, and this algebra, irrational rotation algebra, they are modeling this bad space, so to say. But since this should be viewed as the algebra of this quotient group, this should carry some sort of some symmetry of this group. That's the point, and this was what I was saying in the previous slide, and that's one of the motivations for us, how to understand these symmetries, how this group should act on this algebra. Well, first of all, one could think that this is a quantum group. Maybe we are lucky, and then this is a quantum group, and then we would say, well, this quantum group acts on itself. But that's not the case. So there is a theorem by Piotr Zoltan, I forgot the year, but some 10 years ago also, saying that this algebra does not admit any quantum group structure as a system algebra. So this then we can give up understanding this as a quantum group and some sort of symmetry of this kind. So we are not going this direction because this doesn't exist. So, but then the question, how do we understand this quotient group, this non-commutative quotient group, so to say, and in particular, how do we interpret this, how this group should act on itself, and how should we model this symmetry? That's the point. In general, how do such groups like this, which are badly behaved as topological space, how do they act on system algebras in general? We can ask this question. So actually here in this example, we can say some things that we see that, for instance, in this algebra, we have the so-called classical gauge action, which is an action of the circle on this algebra. Since this algebra is generated by these unitaries, we always have this gauge action. We can take any, we actually have many gauge actions here. One can take one of these is this one here. One can take one of these unitaries and multiply by any circle number, complex number. This doesn't change the relation, so this gives us a symmetry as an automorphism of this algebra. So this gives an ordinary action of the circle, but we are looking for an action of this quotient group. So, well, if we just look at this action, and this should be indeed be somehow lead to the action that we are looking for. When we restrict this action to this subgroup, to the subgroup of these powers, it's not inner. So an ordinary action of this quotient group would be an action of the circle, which is trivial onto this subgroup. But being trivial actually on this subgroup, since it is dense, it would be trivial on the whole group. So that's the point here. In this action here, it's not trivial. It's not trivial, but from the relations we get this, and this means that this action restricted to this subgroup is inner. But it's not trivial, it's inner, implemented by unitary in this form. So that's what I was saying before. This is not an ordinary action of this group. So we should try to do something different here. And that's now the point we are going to understand this better in using higher category theory. So we are looking, we are modeling these actions here that do exist actually in this form. We are going to interpret this sort of behavior here as an action of a two group actually here. So let's then move to this topic now. So so in the case of groups, higher two groups can be modeled by cross modules. This you should probably know from this audience. But let me just remind you about this in any case. So one very basic example of what we call a cross module is a quotient or a group and a normal subgroup. If we have a group and a normal subgroup, we can look at the inclusion map of the subgroup into the group, and we can look at the important conjugation action. Always when we have a normal group, a normal subgroup, we have the conjugation action, and this is one example of our cross module, and also actually this is what's happening in our motivating example. Since we have a billion groups, everything is normal, and we have one instance of this. So this is already in this category. And just a moment here. Yeah, and in general, a cross module consists of a cross modules of groups. I should say consists of two groups. We have one group G, one group I'm calling H, and we have a homomorphism of groups I'm calling delta in general. And we have a sort of action of one group onto the other by group automorphisms, and a sort of conjugation action. And this should behave more or less like in this case of this normal subgroup. So they should satisfy these two relations here. they essentially onto the image of this map, they behave like the conjugation action. Essentially, this is what they are saying. And as I was saying before, our motivating example is in this class. So we can take the circle, and can take the integer, and we can take this embedding, in this case, this homomorphism. As I was saying, we take powers of this fixed number lambda. Lambda was this number that comes from the theta, right? So when theta is irrational, this gives an embedding of z into the circle. So it's a very interesting cross module. From one side is actually almost trivial. Yeah, the conjugation action has to be trivial in this case because everything is abelian, and we only have this embedding. In this case, it's a group contained into the other. Whenever we have two abelian groups, we have a cross module of this form. But it's a dense embedding. This is what makes it non-trivial. And it also, now it incorporates the topology also. Yeah? We are looking actually here, we are not mentioning topology, but in general, we look also at together with the topology. So the circle has its natural topology, and this should be taken into account. So it's a topological cross module. So this is probably trivial for you or well-known for you, and it's a well-known proposition. The cross modules, they can also be viewed as two groups. What is a true group? As a true group is a two with three. I'm thinking of a strict two category here, and where all the morphes and two morphes are invertible. And a true group is just a true groupoid with a single object. I'll say more about this, although I know that you are experts on this, but let me just remind and also fix notation and so on. So what is a true category in general? So in a true category, you have the objects, like in a category, you have the morphes, but we also have the two morphes. And since we are now thinking of a strict true category, we also view the two morphes as bigons of this form. So the two morphes by bigons, these two arrows here. And as in a category, we can compose the arrows. We can also compose the bigons, so the two arrows. But we have two forms of composition. One is the vertical composition. This is somehow pictured like this. We can take two to three morphes and two morphes between them in this form vertically, and then we would get a vertical composition. So this is the data. Yeah? This is given in the category, the true category. And also we have a horizontal composition. Whenever we have a picture of this form, we have two morphes, parallel morphes like this, and we can join like this, and then we also can assign the horizontal composition of the bicon. So this is another data of a true category. And there are some conditions that should be satisfied. I'm not actually writing the conditions, but you can imagine, and you probably know these conditions, so I should not, probably don't need to tell you about this. But now looking at this motivating example, from this point of view, we can look at the circle, and again the integer. This is a cross module. We can view this as a true category. How do we view this as a true category? It's a true group. So it only has one object, which is this star here. This is this object here. Yeah, this is the one object. So I'm drawing this object several times as the same object. So we have between these objects we have several arrows, which are the elements of the circle. Every Z gives an element we think of an arrow. between this object and itself. And for every integer, we attach a bigone between the z and the lambda n z. So this is modeling this quotient, you see. So in this quotient, these two elements would be equivalent. So they would be the same element in the quotient, but now we separate them and look at this class as every pair of this equivalence class gives a bigone. So this bigone, this category, in this true category, contains more information about this quotient. So we separate then it and then view it as a cross-modular two group in this case. And this is the horizontal multiplication, how this is done. So we essentially just multiply the numbers, the circle numbers, and sum up the integers. And also the vertical composition is just essentially summing up the integers and doing the obvious thing in the composition of the arrows anyway. So this is the structure of this two group from the point of view of two categories. Yeah. So how does this relate to system algebras now? So actually we have some two categories of system algebras which are interesting, and we discovered them in these papers. So actually this was already around, but we only formalized it in this way. So these types of morphisms was already researched before. So system algebras are algebras of operators, right? So for those who don't know, just think of a Hilbert space and some subalgebra of operators. So these are the objects of our two category now. I'm defining what will be a strict two category, which I'm denoting C star 2. Yeah? And the objects are the C star algebras. The arrows are almost the usual arrows that we look at C star algebras, but we allow multipliers. So multipliers take into account also non-unital C star algebras, and they behave better in this respect. And we are, for instance, allow it to take unitaries. Yeah. So whenever the C star algebra is not unital, we look at the multiplier algebra to be able to have at our disposal the unitaries. So these are the morphes, the star homomorphes, and also we look at non-degenerate homomorphisms, a technical condition, but it's important. And the bigones here, the bigones are just the essentially unitaries that intertwine the two given morphisms of this sort. So whenever we have two maps from A to B or M of B, we can look at unitaries that intertwine them. So this actually also could be read as saying that G is at U conjugation by U of F. Yeah? So it's conjugating F and giving G. Since U is unitary, it could also put in this form. At U just means that we take F U, F of X, F of A, U star. This is what this means. And so these are the bigones, and of course we can compose these arrows. So it's not quite obvious, but one can compose these things here, because when this is where these non-degenerate C conditions enter, because we can extend to multipliers, then this can be viewed as maps from multiplier algebras, and then we can compose in this level and then view again as maps from A to MB. These are in this sense is the usual composition. And the vertical composition is essentially the multiplication of these unitaries that implement the bigones. And the horizontal composition is slightly more complicated, but one can draw these things and realize that whenever we have two maps that are connected by unitary and two other maps that are connected by another unitary, and then we can compose these two. We have actually a situation like this right here. And then whenever we compose the two top, say, things and the two bottom things, we can realize that there is another unitary that's built from U and V that implements these intertwining conditions. So this is how we define the horizontal composition in these two categories. So, and these two categories exactly looking at these things that in general in a homomorphism, in an automorphism, they are not trivial. So they treat these two categories, treat the inner automorphism as non-trivial. Yeah. So they look at these data and they do not identify, say, because one might say, well, whenever they are conjugated by unitary, maybe they are almost the same, and then disregard this and consider them as the same. But this category, these two categories, it separates them and considers this data. Yeah. And also we have another category, another two category of systalgia, which will be important here. And it's, but it's a weak two category. Probably also, you also know about this. I don't need to say, but I'm only giving as very special example here. There is another special category that we call core 2. Core is for correspondences. So it has the same objects, the system algebras, but now the arrows are more general. So instead of just looking at morphism, usual homomorphism into multiply algebra, we look at correspondences. And correspondences, by that definition, is a bimodule, essentially. It's a Hilbert module over the system algebra, the target system algebra, and it contains now, as before, non-degenerate homomorphisms from A to the adjointable operators. These are the adjointable operators. It gets a bit more technical, but when one studies this, is related, is more or less similar to the weak two category of bimodules and algebras and rings, or rings and bimodules that you probably know. And here the bigons are the isomorphisms between the bimodules, the correspondences. We just look at two bimodules, two correspondences, and then we say there might be an isomorphism between them. An isomorphism is just a unitary. We have bimodules with inner products here, which are system values. So we can talk about unitary intertwiners. Yeah? And here the composition of arrows, and now we can look at the balanced tensor product of correspondences. So if we have two correspondences, A and E and F, say, or H and H prime, we can say one A is from A to B, F is from B to C, then we can form the balanced tensor product in the middle, and this would be the composition. It's similar also to this two category of bimodules of rings. And the vertical composition is here the multiplication of unitaries, and the horizontal composition of the bigons is essentially you take the unitaries and you take tensor of them, and then you can build another unitary. I think there are some questions in the chat. Okay, sorry. What is M of B? Yeah. M of B is the multiply algebra. So yeah, I'm not, maybe you could just think that all algebras, in the motivating examples, all algebras are unitary. So in this case, M of B or M of A is just A if A is unitary. So M of A, M of B, you should think as a unitization of the algebra. It's the largest unitization of the algebra, essentially. That contains the algebra as as an essential idea. Yeah. It's a sort of unitization of the algebra. It's just to put units on the algebra, essentially, to fix this gap. Up to this detail, this category of multipliers would be just the ordinary category, but upgraded with this unitary. So as I said, this is a weak category, so the composition, so would mean if we take now three bimodules, say H and here, this is not actually, so we can take in two ways. This is not equal, but it's canonically isomorphic in these two ways, and this is the associativity, which is not trivial, and it's this associator. The associator is not trivial, so this is a weak two category of system algebra. But this actually is so natural that we sometimes I'll actually identify and just write sometimes just the triple composition because this associativity here is just so natural. Anyway, so these are the two examples of two categories that we are interested in system algebras. And now, since we have this first strict two category and we talked about cross-module, there is a relation between this. So there is a cross-module which is closely related to this category of C-star algebras. This first two category, the C-star 2, where we have this strict two category, we can assign to this category the following cross-module. Essentially, actually, we fix an object of this category, so we fix a C-star algebra, and then we can look at the following groups. So we take the automorphism groups, the group of automorphisms of the algebra, this we call G, and we also look at the group of unitary multipliers. Yeah? If the algebra is unitary, it would be just the unitaries of the algebra. If the algebra is not unitary, we take this unitization, we take these unitaries of this multiply algebra. And then these two groups, they form a cross module. How do this work? So we have what appeared in this category was this conjugation by unitaries. So we look at this junction. So this gives a map. We take any unitary multiplier, we can assign a automorphism. This is the inner automorphism associated to this unitary. So this gives a homomorphism of groups from this group to this group. And the automorphisms of the algebra, they act on the unitary. So if we take an automorphism of the algebra, and if we take a unitary multiplier, we can just essentially extend the automorphism to the multiplier and then evaluate onto this unitary. This gives another unitary. Yeah. So this data here then defines the structure of a cross module, which is closely related to these two categories. And this cross module is in general not trivial. So maybe you know that cross modules, they are classified essentially, at least the discrete cross module, they are classified by some data like the kernel and the co-kernel and something else. And the kernel and the co-kernel of these homomorphs, they are both non-trivial in general. The kernel are the things that you can see from here, the things that are the unitaries which are central, they commute with all the elements of the algebra. And the co-kernel is the automorphic group. They might be non-trivial in both cases. So this is an interesting cross-module. And having this cross-module at our disposal, we can now define actions of cross-modules onto this category directly. This is the reason why I'm doing this. So how now we could define a notion of action of symmetry? Well, we are arriving at this. So since we now have notions of cross modules, let's start with the cross module, the most simple two categories. So we take a cross module. How does this act on a sister algebra? So well, we can just take a sister algebra and look at this cross module that we just had in the previous slide, and then given another cross module, we can look at a map. Amorphous between these cross modules. So this is then our notion. So this would be a notion of action. So what is an action then more explicitly? So an action is what is a morphism of cross modules. Yes, a homomorphism of cross modules is just we have a homomorphism between the group G's. Yeah, so we have a homomorphism between from G to the automorphous group of A. This is a usual group action then. Homomorphism of groups is an ordinary group action of G on A. But we still have a group homomorphism from the other group H to the unitary multipliers, which is the age of the other cross module. And of course, this map should respect the cross-module structure. This means that the delta maps are compatible, and also the conjugation maps. These are the two equations that we need to impose. So this is the definition. This is our definition of action of a cross-module on a sister algebra. And well, let's look at the very special case when you have a normal subgroup. When you have a normal subgroup, this was already known before. We defined this in one of these papers, but this in this special case, whenever we have a normal subgroup of another group, this gives a cross module, a special cross module. And in this case, this is the definition what people call twisted action in the sense of Philip Green. Yeah? You can look for this if you like. This was already known for 40, 50 years ago, maybe. And we just recovered this notion in this case. So one example. So now we can already look back into our motivating example. From this point of view, we can already implement some action, some symmetry. So we can look again at the irrational rotation algebra, and we can look at this cross module, this cross module that only has the circle, the integers in this embedding, and we can define this action now. So the action of G is just the gauge action that I discussed in the beginning. And this homomorphism from the integers is implemented by this map. If you recall, we said that in the image of this map, we had something like like this, I think. And this is why this map here appears. I think I forget here exactly the formula, but this map here, this map is saying that the action restricted to the image here is not it's not trivial, but it's inner by this unitary here. We are specifying how it is inner. We're not just saying it's inner, we are specifying the unitary that implements the innerness of this automorphism. Okay, a more general example motivated by this is the following. So actually this algebra, the irrational rotation algebra, as I said in the very beginning, can be viewed as a cross product. A cross product is a process in the sister algebra world to produce another sister algebra from an action. Yeah? You start with an action of a group on a space, and then you can build a cross product. Like, for instance, the action of the integer on the circle by powers of lambda. This is an action which is related to this cross module, of course. And this gives this sister algebra. This is one way to view this rational rotation algebra. And based on this, we can actually give more general examples. Whenever we have a sister algebra B, this would be the continuous functions on the circle in this case, and we have an action of some group. This would be the group would be the circle here, and the action would be the translation action. We can restrict this action. We start with a cross module. We start with any sister algebra with an ordinary action of the group G, and then we can we can sort of restrict this action to the image of the H group, and this gives another action. And on this algebra, the cross module acts. Yeah, and it's not difficult to specify a formula here. I didn't write it here, but it's very similar to this action here. Yeah. And this gives a very general way to define several examples of this sort of action. So here's a theorem that we proved. We define actions of cross module in this ad hoc way, say, by just saying we have cross modules and then we have maps of cross modules that respect the structures. But we could also have used the category approach, a higher category point of view, and look at maps of categories. Since we have cross modules, they are two categories, and then we have the two functors. And indeed, when we look at functors from one category to another, we recover exactly this definition that we had. So whenever we view a cross module as a category, as a true category, and we view and we look at a functor from this true category to the category C star 2, which is another true category, strict in both cases, and we look at strict to functor between these two true categories, we get exactly a notion of an action of this category onto the object that is assigned to the unit here, to the single object of this category. And just recalling here, a strict functor in this case here is just a map between the objects, a map between the arrows, and they respect essentially everything here, like the composition. So this is a strict to functor, yeah. So they strictly preserve the structure, and this is the notion that we have here at the moment. So now we can also consider weak two categories. And these weak two categories, then we can think in the same way, but we then should not ask for equalities here. This is the difference. So, for instance, let's start again. So if we take a group and we can view a group as a category, and we can look at this true category of sister algebra. If we just look at a strict functor from the group to this sister category, we get the usual notion of action. We don't get anything new. But of course, even in this situation, we can also ask for weak two functors. We can weaken the notion of action. And when we do this, we should, for instance, take this equation here, which is the basic definition of action, and we should replace this equality by bygone. Yeah? And when we do this, we also need to include some coherence laws to make this, because we then add two bygones, we add bygones to the equalities, and then we need to include coherence laws to these equations that we have. So when we do this, in this case of a group, we get the following. We get a map between the group and the automorphism, and for each pair of the elements of the group, we then have a bygone. We replace this equality by, we say they are equivalent in a sense. So in this case, they are implemented by some unitary. Yeah? So and this is a unitary multiplier. And then we need to ask some conditions, of course, this coherence laws that appear, that's some slightly complicated in general, but here they, for instance, when we have an ordinary action, we would have two ways to compose triples of this form. We could first compose the first two, and then arrive at the third composition, or we could compose in the other way and get in the same place. This then leads to, we need to include this as a coherence condition. So we need then, since we are now adding more data, these unitaries are being added, we need to impose a condition of this formula. If we go in this way or this way, and we use the associator of the two categories, which in this case is nothing, but it would be equal, right? But here we need to say that these two unitaries, these vertical compositions, they are equal. And well, whenever, if you work this out and then you arrive at a result that we proved, so we can characterize indeed the weak two functors, the weak functors from G to the C star 2. The most simple case would be exactly this. We start with a group and take this strict two category, but we now look at weak functors between them. And then we get exactly the previously defined Busby-Smith-twisted actions. These are, this was already known before, and they are given by the following data. We have automorphism and we have these unitaries, and they satisfy this. This is exactly saying that we have essentially a bygone of this form, right? We have a bygone in this way. And also here we have these conditions. We add more conditions to get this action, but anyway. And this is this here is related to this coherence condition here. So this is a sort of, this is complicated, and when we look at this from this equation, just from this equation, but from the point of the higher category, this is essentially this higher associativity that we get here. I think I'm finishing. I don't know how much time do I still have, but it's almost the last slide, I think, here. We can also do the same process for groups and this weak two category of C star algebra. Instead of C star 2, we take this correspondence category. And then we look at the same sort of functors, the weak functors. We get another well-known notion from the C star algebras, which is the notion of Fell bundles. Fell bundles, they are, for those who don't know, they are essentially these actions, these weak actions onto these categories. And for those who know these Fell bundles, this is then a theorem. This is Fell bundles, they are equivalent to actions, to weak actions. So there is the definition of Fell bundles here. they were given by FEL, but I think I don't want to spend too much time on this, but this is what comes out. And of course, we can also do the same things for higher categories like cross-module, more general cross-modules. And we can look at either C star or the correspondence category, and we describe what happens in each case. So in general, we get FEL bundles over these cross-modules. I describe it here. It's not very important, but the moral of the story is that we can describe them somehow. And maybe I say more. Can I take more 1 or 2 minutes, Juan? Is that okay? I think I'm.
Yes, please. Yes, yeah. Take as much.
Okay. So. One important thing is whenever you have an action, as I said before, we can build a cross product. This is the most interesting object whenever you have an action from the point of view of C-star algebra. And we can also do this for these higher symmetries, higher actions. So we define in these papers, we also could define the cross products by these cross module actions. And there is one of the results that we proved is the following. So related to this example that we start with a C-star algebra in action, we restrict it to the image of the age group, and then we can describe this cross product, which is being denoted here. This is the cross product, this new cross product. Applied in this situation, it recovers the original cross product. This is what this theorem is saying. Yeah? So we can apply this to this motivating example to compute the cross product. The cross product of the irrational rotation algebra by this cross module at the end is the algebra of compact operators. This is maybe not very interesting and at the end, but this is what happens. And also we have some results about the strictification and stabilization of these actions. So essentially we can prove that every weak action of a cross module can be strictified. It's equivalent in a sense to an ordinary strict action. And when we apply this to the theory of FEL bundles, we can say that every FEL bundle is equivalent in a sense to an ordinary sense, to an ordinary action. And this is in the sense of Morita equivalence, because we now look at the correspondence category. Well, this is the summary and the end of the talk. So essentially we describe cross modules, the quotient groups, they may be described by cross modules or 2 categories. And hopefully speaking, the action on C-star algebras, we define how they act on C-star algebras, yeah, by essentially by these homomorphisms that are specified by these unitaries. And also we could, on one hand, interpret certain well-known concepts from the higher category theory. So this gives a new perspective for these results, these previous well-known results. So that's what I had to say. Thank you.
Yeah, thank you very much for the beautiful talk, Alcides. Yeah, so does anyone have any questions or comment for Alcides?
I have just 2 questions. But one, let me make me precise. It's about this classifying functor. So we have this functor that classify a category. So I some time before I was to introduce the classifying functor in yeah, in non-commutative geometry, and I was interested in this in the quantum torus. The quantum torus is the cross product of the circle with an axiom of the integers, but the circle is the classifying space of the integers. So I was some curious if there is some the looping process. Maybe we have to put this in the two-level categories that we have at the looping of the circle, and then we have a semi-direct product of a category, maybe the two in the two types, and by the integers, and then the classifying space of this category is the circle, but the classifying of the whole thing is the quantum torus. Yeah.
Mm-hmm.
Yes. So
it's a good question. Probably something could be said in this direction. Unfortunately, I cannot say anything in this about this. But I think Ralph had some student that maybe did study something related to this. One of the goals was also try to view, maybe this is more or less this classifying things. Like in sister algebra, we usually classify things in terms of K theory or KK theory. Maybe this is related to this, I don't know. And there was an idea at some point to relate this to also to higher category, but I don't know exactly to which point this was reached. So I was not involved directly into this project, but I think there was some work, and I don't know whether they published something. Maybe this is related. I just speculated. Really don't know much about this in this direction. Sorry.
No, so the thing is that when you apply the last classifying space, for example, you finish with the torus because.
Yeah, this is interesting. Yeah. Probably there's something there that should be understood. A good question. I don't know.
A second question is, well, you mentioned this theorem of Picht, that the rotation algebra admits no quantum group structure, but there is any relation with the harmonic oscillator,
Oh, the harmonic oscillator, you mean some physics, you mean? The harmonic oscillator? Oh, good question. I don't know. Well, I don't know. I don't know of any relation with the harmonic oscillator. You mean the irrational rotation algebra relation with the harmonic oscillator from physics? I've never heard about this. Not that I know. I know of no relation with this. So the irrational rotation is usually, as I said, interpreted in terms of quantum tori or quantum space related to this rotation, but not to the harmonic oscillator. Not that I know. I think there is no direct relation, but no one knows. Maybe there is. Yeah.
Yeah, does anyone have any other questions or comments? So we have a couple of, well, actually comments on the YouTube chat. So Matthew is
Where?
So we're live in YouTube. So I have to ask the question myself.
Ah,
That's
okay. Okay. I'm not seeing these questions. Yeah, sorry.
Well, so he mentions that there are many parallels with the Mackey machine to classify projective unitary representations of a group. So using projective unitary representations of certain normal subgroups and quotient groups. And so he mentions that the projective unitary representations are basically unitary representations, but you sort of lose the strict relation. So I suppose that's related to the Busby-Smith.
For the actions, in general, the actions on compact operators, they are related to projective representations. And this is also related to these twists that appear in the theory. Yeah, this is related to this stuff. Yeah, a good observation. Yeah.
So, do you think there's a way of putting this in this sort of weak action on a
yeah? So the twists they appear as these bygons in this category. Yeah, these appear already in these Busby-Smith twisted actions, and they are related to these projective representations. Yes.
Yeah.
But this is the relation. So.
Okay.
Yeah, the data, essentially the data of this category, they are in this way.
Okay. Yeah. Thank you. Well, so there is another question. So, are there any detailed lecture notes available on this this question?
Oh yes. There are some lecture notes by Ralph who gave some extended lectures somewhere in if you Google these lectures on non-commutative geometry, Ralph Meyer, you should find this somewhere. I remember that he gave some extended lectures, I think almost 10 years ago already, in Argentina. There are, I think, some lecture notes, and also we gave, but I think there were no written lecture notes in IMPA in Rio de Janeiro, me and Ralph, but I think we didn't write lecture notes. But there are these lecture notes by Ralph and from Argentina some years ago.
Yeah, is there a comment? Okay.
Yeah, I find this, but you should just Google this and you probably find.
Okay. Yeah, those. And there was the unpublished book on this by Ralph as well.
Yeah, there is also an unpublished, still unfinished book about this and more other things from Ralph also as well.
Yeah.
And he's writing this book for many years already, but he didn't finish it yet. It contains all this stuff and many more other things. And also probably in YouTube you'll find lectures by Ralph related to this.
Yeah. Yeah, does anyone else have any questions or more comments for Alcides? Well, I do have so we already talked privately a bit about possible extensions of the program to, especially to inverse semigroups and non-saturated file bundles. Well, could you please, and of course to von Neumann algebras. Yeah, could you please comment a bit on other possible extensions of the program, maybe other two categories or bicategories of C-star algebras or something more general, or?
Yeah, so we also have some works, I didn't talk about this, we have some joint work with Ralph where we also deal with this, for instance, when you replace a group by an inverse semi-group, and then we describe the same, we prove the same theorem, essentially stating, for instance, that we describe functors from an inverse semi-group to another bicategory. Actually, now we have to specialize we don't look at the whole two category of correspondence. We look at the bimodules, the invertible bimodules essentially, the partial imprimitivity bimodules. So these are nicer correspondences. And if you look at these weak functors, we describe these weak functors in terms of cell bundles also.
Okay.
And we left open the description of the weak functors from the inverse semigroup to the C*2 category. And but this should also be related to the Busby-Smith actions in the same way as groups. Of course, one can also try to go further, say cross modules of semigroups, inverse semigroups, try other stuff like this. And also change, instead of C** algebras, look at von Neumann algebras. There are related things about von Neumann algebras. Of course, there is then the well-known notion of actions, but there are also cell bundles and so on. And so there are a lot that one could try to extend. And, of course, it would also be nice to see other applications of this. I just Googled here at YouTube. There are some lectures from the Hausdorff Center for Mathematics from 2014 by Hals on non-commutative symmetries of C** algebras. In these lectures, Hals should also, I don't remember, but also is related to these other questions.
Okay, yeah, I can look. Well, maybe you can. Maybe I can look for them and I'll post them in our site, so they can.
And also put in the chat if you want here. For instance, this one.
Okay. Oh yeah.
Hals-Meyer symmetries in non-commutative geometries is related to this same talk that I'm giving today. But there are much more information there because he gave, I think, 4 or 5 lectures.
Yeah. Yeah. Well, I do have another question, just less. So, yeah, it's so the first time that I saw it, I thought it was a very beautiful program, and I've seen that it's very well appreciated. I've talked to a lot of people, well, not a lot of people, but some people that really appreciate it and do like it a lot. So why did it stop?
Oh, it didn't stop, but as I said, we are still doing something more or less in this direction, but we didn't develop further some directions, but others, yeah. So we are doing right now so there is we still have a project to what is still not known. For instance, it's still a problem. Is if you take a true group or true groupoid, yeah, then it's maybe I stop sharing here because it's making. If you take a true group, you can certainly define an action on the complexes and then define its C* algebra. So if you take a true group or true groupoid or cross module, you can use this theory that we have to define the C* algebra of the true group. Sometimes it's trivial. If you take this C* algebra of this integer embedded in the circle group, you get the complex numbers of the C* algebra. But that seems to be what it should be. On the other hand, if you go a bit further and if you just take any weak true group, say, or weak true groupoid or bicategory or something like this, we would like to have also a C* algebra assigned to this. This is still not clear what that should be. And also in this program, we only did it only for strict two groups, so cross modules. We didn't study further the general weak two groupoids, say, which are best modeled by categories in terms of CAM complexes and so on. So this is still ongoing project. We have an idea how this should be done, but it's still not clear some details. So we are doing in step by step by rediscovering the representation theory of groupoids. We have already a paper from 2 years ago, I think, where we deal with the representations of groupoids or ordinary groupoids from the point of view, more or less from this point of view, but we don't include explicitly the categories. And then we now are finishing a paper about representations of cell bundles of groupoids, where we also use this. And the third paper of this series then would be to include the general cell bundles of bigroupoids, so to say. And this would give this thing, but it's still it's going slow because. But still researching on this.
Yeah, another possibility that I don't know. I talked to Luis a little bit about his theory of inverse semi-groupoids. And he mentioned he has this very long paper and so on, which I was trying to read, but I didn't get to read it yet. But is there any direction this can go with respect to inverse semi-groupoids?
Oh, good question. Probably, yeah. As I said, one can go further and further.
Yeah, I think you can go as far as you can.
Inverse, what should be an inverse bigroupoid or something like this? And probably there are some things that one can do, but it gets so general that's also gets more complicated.
Yeah.
But certainly one can do something in this direction,
yeah.
We also consider these things semi-groupoids and stuff like this. But one should, in general, first maybe look at examples and application, what one wants to do, instead of maybe let me just generalize things and have no application for that. That's the problem.
Well, one thing I thought you could maybe there's a chance to do, which is not just generalized like a senseless, is so in my talk in UFSC, I talked a bit about these double categories. When you try to put the symmetric monadal structure on Bohemian algebras and so on, and you try to extend. So you can do this with correspondences pretty easily. So the balanced tensor product is functorial and so on. So there's no problems with this. So you can sort of put the two categories into a single thing where morphisms are not bigons or squares. And so maybe a possibility is to think, so this is so think about, there's also double groupoids. So you can think about the actions of double groupoids. And then maybe there's a way of combining the two, the Busby-Smith and the Green twisted actions in a single kind of action where you act by squares and not by bigons. So maybe that's a little bit less senseless.
The Green and what? What you want to do?
So sorry, so if you have